Alright, so in this video what we're going to take a look at is a end of topic assessment for the thermal physics part of the A-level physics course. So we're going to start off looking at some specific heat capacity. So what it says here is we've got lead has a specific heat capacity of 130 joules per kilogram per Kelvin. What does that statement actually mean? So what that actually means is it would take 130 joules of thermal energy to raise the temperature of 1 kilogram of lead by 1 degree Kelvin. So what we're looking at there is really what the definition of specific heat capacity is. So this next one we're going to look at how we can apply that. So what we've got is we've got lead, and it's currently in its solid form because we're going to raise it to its melting point. And so it's starting at 21 degrees. And its melting point is, as we can see here, 327.5 degrees. So we're going to get put some energy in to change the temperature, and then we're going to look at the energy it's going to take to turn it from a solid to a liquid. So first of all, the energy to raise the temperature of it is going to be using the specific heat capacity equation. So E equals mc delta T, or you might have seen it as Q equals mc delta T. This one here we got given in part A, so you need to pick that up from the start. We've got the change in temperature, we've got the mass, and we can calculate what the energy change from that is. And then the energy to actually change the state or change the phase of the lead from solid phase to liquid phase is going to be Q equals ml or E equals ml. So that's what we can see there. And because you're going from solid to liquid, you want the latent heat of fusion. The latent heat of vaporization is for going between liquid and gas. So that gives you a value. If you add those two values together, that gives you this value overall here. And if we look here, your mass was 2 sig figs, your temperature here was 2 significant figures, so your answer should be given to 2 significant figures there. Okay, so that ends looking at the specific heat and the latent heat section of thermal physics. What we're going to look at next is actually looking a bit more at the experimental gas laws. So what I've done, this is a longer answer question. So what you had to do is explain how they found out, or you would go about finding out absolute zero. And there are these 4 key criteria you have to show in your answer. So what I've done is I've written my answer and I've highlighted the parts that are relevant for the different points that you need to give here. So you can see from the points that they're asking you to give, this isn't really a practical focused question. This is on actually looking at the theory behind it more, because they're talking about not giving full details of the apparatus and stuff. So they're looking more at the theory here. So do flick back if you want to know what each of the colours mean, but I'll press on and have a look at the next one. Okay, so to start off with, the way I'm going to go about doing this is keeping the pressure constant and the number of molecules of gas constant, and I'm going to vary temperature and look at the impact of that on volume. So if you're going to keep the number of molecules constant, what you need to do is have a sealed container. So I picked a syringe, and what you can do is melt the top of a syringe so it's completely gas tight. So that's what I'm going to go for as my sealed gas container. You could literally pick anything you want. You don't need to be too detailed here. And the reason you do that is you want to keep the number of molecules or number of moles of gas constant. Because remember, essentially the equation we're looking at is PV equals nRT. So in terms of things that are already constant, N is already a constant. R, if we're sealing the syringe, R is a constant anyway. And so if we want to look at the relationship in this one between volume and temperature, what we also need to do is keep pressure constant, and I'll explain how that works later on. Okay, so we're sealing the syringe, keeping the number of moles constant, and what we're going to do is we're going to use a water bath as a method of giving very controlled temperature changes. So if you're going to do any kind of detailed experiment and collect data, you need controlled temperature conditions, and a water bath is an ideal scenario for that. So what you're going to do is we're going to set the water bath to a certain temperature, I don't know, 30 degrees. and we're going to put the syringe in it, and we're going to leave it in there for a period of time to allow it to become the same temperature as the water bath. And then at the point it's become the same temperature, what we're going to do is measure the volume. So syringes on the side have a volume measurement, so you can actually see it directly from the syringe what the volume of gas is inside it at that temperature. And then what you're going to do is you're going to change the temperature and look at what the volume of the syringe is at each of those temperatures. Now, with a syringe, you know there's the plunger end, which is free to move, so you need to make sure it's not obstructed in any way. But the syringe should equalize the pressure normally, which is why I picked a syringe here, or something like a piston would work easily as well. So that's how we're going to control the pressure. We will allow the syringe to expand so that pressure inside equals pressure outside. So if you just leave stuff and allow them to expand, they will equalize the pressure by themselves, so we don't have to worry about it. So I've suggested here a suitable range of temperatures. Like now I'm looking back at it, because it said it wasn't really very practical focused and looking at apparatus, this probably wasn't necessary, but I was thinking about it, so I wrote it down. And then what we're actually going to do is you're going to be, obviously we said we're looking at the relationship between temperature and volume. We said we're going to measure volume from the syringe, so we'd go about measuring the temperature. I'm going to pick a digital thermometer because they usually give you a better precision than a normal mercury thermometer. In terms of how we'd find absolute zero, what we'd do is plot a graph of volume versus temperature. So let's see. If I put it on the Kelvin scale like this, volume should be directly proportional to temperature. So all the values you're going to measure will be at the top end, sort of up here. So you'd end up with, I don't know, 7 values. You're going to be very much over here because you're all above room temperature. But what you can do is you can extrapolate it back, and you're essentially looking for where the intercept with this axis is. So this is your volume. This is your temperature, and what you're looking at doing is seeing where essentially this would hit T equals and V equals 0 here. So extrapolate it back to see where it crosses. In terms of the last point, looking at how we can get a valid result. So the pressure we're sort of dealing with under a small amount of water with a syringe will be fairly low pressure air. So the atmospheric pressure isn't that high. So that's one of, and what we're also dealing with is reasonably high temperatures, so we're going to be heating it up. And low pressure and high temperature will not allow the intermolecular forces to affect the results very much, so it will behave quite like an ideal gas, and so it will actually give you a very valid method for doing this experiment. So high temperature and low pressure are the kind of candidates you're looking for things to model as ideal gases. Okay, so let's move on to the next one. So state 2 assumptions about the movement of molecules that are used when deriving the equation of state PV equals 1/3 nm mean square speed. So first of all, during that process, the first thing you look at is the impulse that acts on the wall of the container, and one of the assumptions you make is this one, that essentially it bounces back with the same speed, so you assume it's an elastic collision. In working out the time for that momentum change, you assume that it takes no time or negligible time to actually collide with the wall of the container. When you're concluding that there's equal components in the X, Y, and Z directions, when you're going from the mean square speed in the X direction to the mean square speed in all directions, you assume that the particle is random. And one of the things that's sort of underlying the whole thing is you're applying Newtonian mechanics to it. And Newtonian mechanics doesn't work as you approach the speed of light. So what you're assuming is the gas particles are non-relativistic or not near the speed of light. So we can apply Newton's laws too. So that one is an option here as well. And then what it wants to do is calculate the average molecular kinetic energy of an ideal gas. So we've been given that, calculate the temperature. So you should have this equation to calculate the kinetic energy of one molecule of a gas. So if we know what the kinetic energy is, we know the Boltzmann constant, it's in your formula sheet, we can calculate that the temperature is 3.2 times 10 to the 2, so around 320 Kelvin there. Remembering this equation gives you a temperature in Kelvin. Okay, so in this next one we're going to look at inflating a life jacket using a carbon dioxide cylinder. It's a fairly unusual way of inflating a life jacket, but why not? So we've got currently all the gas is sitting inside this carbon dioxide cylinder, and what we can do is we can open a valve which allows it to expand into this whole life jacket volume. So it says the cylinder initially contains this number of molecules and a temperature of 12 degrees centigrade, and it occupies a certain volume. Calculate the initial pressure. So because we've been given the number of molecules here, we're going to use this equation here, which has big N, so the number of molecules in it, and we're just going to rearrange it to make P the subject, plonk a load of values in, remember to convert your temperature to Kelvin, and then that will give you a value in pascals at the end. So when you actually inflate the life jacket, we've got the pressure falling, but the final temperature is the same as the initial temperature. So if the temperatures are the same, you can use this relationships here, because we know PV equals nRT, and if T is a constant, N's a constant, and R's a constant, we know the PV is going to be a constant, so we can get this relationship here. We know this P1V1 was equal to this one, so that I've put that in there straight away, so we're not using rounded values from the previous answer. Plugged in the numbers here, and we end up with this value here. This is a new volume of gas, so it's expanded into a bigger volume. Calculate the mean molecular kinetic energy of carbon dioxide. So we know the temperature, so we can apply this equation right here. So kinetic energy is 3/2 kT. Plug in the values, convert to Kelvin, and you get a value here. So you'd expect it for like the mean molecular kinetic energy, or the average kinetic energy for one molecule, that you'd expect to be a very small number. So that seems perfectly reasonable. Okay, so then explain in terms of kinetic theory model why the pressure drops when the carbon dioxide is released into the life jacket. So I'm just going to quickly show you a diagram. So when we looked at deriving this, we did it by looking at a cube of air, essentially. So what we were looking at doing is when we were calculating the time, we used this distance here, which to go back and forward, which was 2L, and we divided it by the velocity to give you the time. So we did that with a cube. Now, if you increase the volume of the container, so it's gone from just being in a cylinder to filling now all of the life jacket, what we've done is we've increased the volume of this container, or increased the size of this container. The effect that's going to have is that's going to cause this value here, the L, to increase. So if you increase the L, what you're going to do is increase the time between the collisions, and plugging that into the force equation we had, so we had the change in momentum over time. If you increase the T, what you're going to do is you're going to decrease the force, because the velocity is going to stay the same because temperature remain the same. So the top line stays the same, bottom line increases, so force decreases. Now pressure is force divided by area. So if force decreases, pressure will decrease. And also, if volume decreases, the area at which the force is acting is going to, volume increases, the area it's acting is going to increase as well. So that again will cause the pressure to decrease. So both the force and the area will act to decrease the pressure. So that's the way to think about it in terms of the kinetic energy derivation. Okay, so let's look at the last part. Okay, so explain why the kinetic theory model would apply more accurately to the gas in the inflated life jacket compared to the gas in the small cylinder. So I talked about this a bit earlier, that things behave more like ideal gases at low pressure and high temperature because essentially intermolecular forces will not be as much of a factor, or they'll be smaller. So if you have a higher pressure, that forces all the molecules to be much more closely packed. And more closely packed molecules will have a larger intermolecular force between them, so that will make it behave less like an ideal gas, and so the kinetic theory model, which assumes it's an ideal gas, wouldn't be as appropriate. The other way you can sort of think about it is well, it's fitted into a much smaller volume, so the particles are much bigger relative to the size of the container, and one of the assumptions in kinetic theory is that objects, the size is small compared to the size of the container, so it becomes less effective a model because that stops being true as well. So there's two ways you can think about that one. In terms of the first law of thermodynamics, explain how the temperature of the gas in the system can be the same at the beginning and end of the process. So the first thing is, if temperature is going to remain constant, internal energy must remain constant, because the two things are directly proportional to each other. One can't change without the other. So in terms of the first law of thermodynamics, that looks like this. So the change in internal energy is going to be equal to the heat energy added, subtract the work done by the gas. So if we know the change in internal energy is 0, because it stays the same, we know that heat energy added is going to translate to work done by the gas, so we don't get a net increase in internal energy. So the gas is expanding, so it's going to be doing work on the surroundings, so it takes work to inflate the life jacket. So in order for that to happen, it must have been supplied with some thermal energy to keep the internal energy the same, so that it must have been heated in some way or taken heat from the surroundings in order to allow it to do that. So that's how that works there. So that concludes this end of topic assessment and this video.